the podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to do a little AP Plus for Chapter 2, Section 8. And 2.8 involves a lot of equations and math about work.
So we're going to look at the math behind the topics that we've been talking
about. And energy. And of course that comes in the three forms we talked about: kinetic, gravitational, and elastic potential. And so we're going to get into that a little bit and show how this all ties together, and how by doing work on an object you give it energy, and how energy is the release of the work, and et cetera, et cetera. So I'm on page 228 as I start here, and I'm going to start with something really simple. I'm going to start with the work equation, which
also just work is force times distance.
Force times distance, yeah. And so if I do work on an object and I lift the object up over my head. All right, so here's my object. All right, this took force for me to do. Is that correct?
Correct.
So F.
And you moved it over a distance.
And I moved it over a distance D.
So you've done work.
So I've done work. So yeah, check. Work is done. Now, while I'm holding it, I've already lifted it. While I'm holding it, am I doing any work?
No, because
No.
you haven't changed the distance.
But what have I given this object? I've given it some
potential energy.
Height.
Right.
And because of that height, I have given it some potential energy. So the gravitational potential energy is, well, yes, it has a mass, and its acceleration due to gravity is constant, and I've
got a height.
given it a height.
Right.
And what's really interesting about that is, if you look really closely, we have a force here. Well, mg is a force, isn't it?
Right.
It's the force due to weight. And distance and height.
Height is a distance.
Yeah, height is a distance. So what we end up seeing here is that work can equal gravitational potential energy. So when you lift you do work on an object, you lift it up over your head, you're giving it gravitational potential energy. So F times D can be, or is, mgh. And if you really wanted to check out the units on this stuff, maybe I should do this in a different color, but just you separate the line there. It's a kilogram times a meter per second squared times a meter. And you go back and you remember what force units were. Well, a Newton is a kilogram times a meter per second squared, and then times this other meter. And what do we have? We have identical units to verify that work can in fact equal gravitational potential energy. And so this is called a joule. So this is 1 joule. That's interesting. So work energy theorem sometimes is what this is called. This works for kinetic energy too. If I do work on an object, that means I've done a force over some distance.
Mm-hmm.
So if I'm pushing on something, there's another beautiful art representation here, and I've moved it. So I'm applying a force, and I've moved this object some distance d.
Mm-hmm.
I've done work.
Right.
It's moving though, isn't it? So what kind of energy does it have?
Kinetic.
This has kinetic energy, or half mv squared. Now this is quite a bit trickier than the previous proof, but we start with it anyway. So did not mean to do that. Let's undo, and let's just get rid of that for the time being. Well, force is equal to mass times acceleration, and I'm still going to multiply times the distance. And now I'm going to rely on some stuff that I've learned in the past, let's say Chapter 1, maybe Section 2 of Chapter 2, where I remember that acceleration was the final velocity minus the initial velocity divided by the time.
Mm-hmm.
And I remember that I had an equation where distance could be the average of the velocities, initial and final, so average, and then I could multiply that times the time. And I have an enormous mess to deal with here, but as I work some of this stuff out, what I notice is my times cancel, Okay, I've got a half term, I've got an M term, and then I've got to do some FOIL. And what ends up happening, and I'm going to skip all of the messy details.
Let's get velocity squared.
Right, is that I get some velocity squared terms that fall out of this. And what I determine is that the work done on my object is equal to the change in the kinetic energy, which is exactly what makes sense. If the object starts at rest, it's not moving, right? So its initial kinetic energy is zero. And then I've pushed on it and accelerated it with a force, and I've given it a new final velocity, which isn't zero. So, in fact, work can equal the kinetic energy. That's pretty profound stuff. And that's why I like physics, because it all pieces itself back together. You know, we've talked about Newton's laws, and then we're talking about energy conservation, and we tied in all this motion stuff that we learned from the last chapter. So you're 8 weeks into your first physics class, and you already see that everything depends on everything else.
Right.
Let's do a couple problems then. I'll let you guys look at the sample problems. Actually, it looks like we're going to have to do one because they don't give any real problems. So let's look on page 229. It says your teacher gives you a pop-up toy. When you push down on it, it sticks to the desk for a moment and then pops into the air. If the toy has a mass of 100 grams, now that is 0.1 kilograms, and leaps 1.2 meters off the table, so it's got some 1.2 meter height, how much potential energy does it have at its point of maximum height? And they want to know about the potential energy, which should be measured in joules, and they tell me to use a value of gravity of 9.8 meters per second squared. So here's my table, here's my pop-up toy. Okay, it has leapt into the air some 1.2 meters. Now, at the top of its path, how fast is it moving?
0.
Right, we knew that already. So the velocity at the top is 0. So how much kinetic energy does it have up here?
0.
0. My pop-up toy. Well, we can talk about elastic energy, and I think we're going to in a few minutes. Does it have any elastic energy?
No, not now, not at the top.
Because it already released it, right? So what kind of energy does it have since it's off the table?
Gravitational potential. It's
Gravitational.
going to change into kinetic, but right now it's gravitational potential.
Potential energy, very good. So I just use my gravitational potential energy equation, which of course says mgh. Well, I've got 0.1, and I've got my 9.80, and I've got my 1.2. And when I multiply all that out, the book tells me that the answer is 1.18 joules. And I encourage you to check that out in your graphing calculator. I'm not sure where the problem is going to take you, but I'm going to take it to a couple different places. I want you to remember this slide here, this picture. And my new question is, how much kinetic energy at the bottom? So I want to talk about the moment, okay, that it leaves the table. So notice it's not touching the table. I want to know about this first moment when it's not leaving the table, it's on its way up.
Oh, that's an easy question.
That's an easy question. So how much energy did it have at the top?
1.18.
Right. How much energy does it have at the bottom?
1.18.
So the kinetic energy as soon as it leaves has to be 1.18 joules. It's already released its elastic potential energy, and now it's on the move.
Right.
We know the mass to be 0.1 kilograms. Okay? And a logical question would be, hey, how fast was it going as it left the table? Well, I've got an equation, right? Ke is half mv squared. I know that the kinetic energy at the top is
0.
because it's not
moving.
Right. And so, hey, I know the kinetic energy, and I know the mass. So I do a little algebra, okay? And I work my way through this, and I determine the speed. So 1.18 times 2 divided by 0.1, take the root of the whole thing, and what do we get? according to your book again,
4.9 meters per second.
4.9 meters per second. And so I have one more question. If the kinetic energy was 1.18 joules after the toy has changed its shape and released its elastic energy, and it had 1.18 joules of energy at the top of its path, I want to go back to my table, and I want to know how much elastic potential energy when it's sitting on the table.
Oh, after it's hit the table?
No, before it takes off.
Oh, it has to be the same.
It has to be the same. So according to energy conservation, elastic potential energy is converted into kinetic energy, which is converted into gravitational potential, back into kinetic, and then it does work on the table.
Right.
Notice these equal signs. The energy throughout the entire process has to be 1.18 joules. There is no other answer to that question.
I know that this is a plus and not a regular, but really this is the essence of a pendulum. It switches from gravitational potential to kinetic to potential to kinetic.
Kinetic, yeah. And there's all kinds of examples of this out there that you can look at and see. Now the book goes on and it talks about spring constants and the elastic potential energy equation. I think at this point you can kind of work your way through that since we've given away the heart of the thing of 1.18 joules. And I encourage you to work your way through the rest of sample problem 1 and take a look at sample problem 2. So with that said, signing off, this is Mr. White.
And Mr. Sadler.